that the CL alpha is no longer a curve. It's no longer 2 pi alpha, but it's now a dynamical system, right? You can write a transfer function, a differential equation, whatever representation of a dynamical system. It's no longer the usual CL alpha curve that we used to. Right? This is no longer the case. This is for a steady case. Ours is a dynamical system. We also derived the Kotta-Jakovsky-Lift theorem, which mainly states that lift is essentially due to circulation, due to the curvature of the fluid around the airfoil. Okay? So gamma, the circulation, is a global measure of the curvature of the fluid around the airfoil, and the lift is essentially due to that. We also derived that this circulation, this global rotation of the fluid around some contour in an inviscid fluid is just zero. So anything can change, the airfoil can do some maneuvers, but the circulation around some enclosed fluid, fluid enclosed by some contour, closed contour, just time varying, this is zero. So these two statements, the lift is essentially due to circulation and the rate of change of circulation is zero. These two statements imply that for a circulation to show up around the airfoil, gamma bound, which will result in the lift, for a circulation to show up, another circulation, perhaps in the wake, has to show up, right? So that the total circulation remains the same inside some fluid bound. Okay? So this in turn implies that the lift has to be time varying. The lift as a function of time will increase until it meets the steady value after some time, as this guy sheds away. Okay? When the wake, or what we call the starting vortex, shed all the way, the lift or the airfoil will be only affected by the bound circulation, and your lift reaches its steady state value. Okay? And we concluded by unsteady aerodynamics, or unsteadiness, is simply the wake effects. If your model accounts for wake effects, your model is unsteady, otherwise your model is not unsteady. You're trying to cheat or make things work, but you don't account for the essential physics. So this was the summary of the first lecture. Any question about that? And I'll show you some interesting pictures from Prandtl water channel early on. So this is Prandtl flow visualization, his channel, long time ago, early 1900. And you can see here, this is the very early moments right after start of the flow around an airfoil. So this is the transient, this is the pure unsteady aerodynamics. You can see here that indeed there is a starting vortex forms at the trailing edge. You can see it, look at it. So this is a flow visualization. We can see the starting vortex, we cannot see the corresponding circulation around the airfoil because there is no vortex, okay? But here there is a vortex. And this vortex, it starts at the trailing edge. We're going to study its physics later on. It starts at the trailing edge, grows in time while shedding away, and grows more and more in time as it sheds away. What happens if this guy grows? What happens? If this guy grows, what happens to the circulation over the airfoil? If the starting vortex grows, what happens to the circulation over the airfoil?
Becomes less.
Grows as well, they have to be equal, right? So the circulation over the airfoil grows, what happens to the lift? It grows as well, it's simply rho u times this gamma, okay? So the lift grows as this guy grows, and this guy does not only grow, it grows and sheds away, so its effect on the airfoil becomes less and less, okay? So the lift grows due to the fact that the bound circulation grows and the wake vortex sheds away, becomes less effective, okay? Until this guy sheds all the way, then the lift is just affected by the bound circulation, the steady state value of the bound circulation. So I'll show you some other pictures emphasizing the same thing. So this is later in time. You can see here, this is the last set of pictures I showed you. Here there is another set of pictures later in time. So the starting vortex shed away, and you can see now you reach the steady state flow. You can see we will come to this later on when we discuss the Carter condition. But now in the very first moment there is a flow from the lower surface to the upper surface, which forms the starting vortex. But when we reach the steady state, you can see here this steady state. There is no flow from the lower surface to the upper surface or vice versa. There is a smooth flow off the trailing edge. Okay? Because this is essential to understand the physics later on. This is the physics of the Carter condition. Here we have the camera is moving with u infinity. So no, this still here is just showing the starting vortex, and yeah, it's just showing the starting vortex, how it forms, grows while shedding, and shed all the way. Here the camera is moving with the u infinity speed. So if the camera moves with u infinity, everything becomes more clearer. You can see here, here's the starting vortex clearly, because there is no, it's as if you subtract, every fluid particle has a u infinity plus some disturbance. If you subtract the u infinity, then the disturbance becomes clearer, right? The disturbance due to the presence of the airfoil in the flow. So here it's as if we're subtracting u infinity from everywhere, focusing just on the disturbance. You can see the starting vortex clearly in this sense, and the bound circulation in that sense, right? And here the same. Now it's after some time, the starting vortex shed away, and you have the bound circulation. And by the way, while it's shedding away, it grows, okay? So as such, the bound vortex, the bound circulation also grows. This is a vortex. This is a vortex. It's free to move with the flow. This is not a vortex, okay? So it doesn't move with the flow. And Prandtl does an interesting thing to prove this even more here. So this is the same picture like this one or that one, but at a higher angle of attack. So at a higher angle of attack, the circulations are stronger. Okay, so you can see the starting vortex here is much stronger than this guy, and also the bound circulation. But then he does this interesting thing. Look at this picture. So the airfoil was moving and then suddenly stopped. Okay. So what's the steady state condition for this airfoil? It was moving with some angle of attack. So while moving with some angle of attack, the steady state condition is some bound circulation and lift. If you stop, what's the steady state condition? No bound circulation, no lift. If you look at it on the airfoil, there's really no circulation. And if you start, a while ago we were having a vortex here, the old starting vortex, and some circulation. They cancel each other. Now we don't have something here, so we shed another vortex. So the total vortices in the wake is equal to the circulation over the airfoil. Here is 0 and here is 0. You see what I'm saying? So at the beginning we move the airfoil, we shed a starting vortex, and we have a bound circulation. The total The total circulation of all the domain is 0. One starting in the wake and bound circulation over the airfoil. Now we stop this guy completely. Okay, so there is no circulation over the airfoil anymore. And due to the change, whenever you have a change in the condition of the airfoil, we're going to shed something in the wake. So when we start at the beginning, we shed the starting vortex. When we stop, we're going to shed another, we're going to call it starting, but it's in the opposite sense. Here are the two vortices in the opposite sense, in the wake, and there is nothing on the airfoil. Okay? You start the dynamics. So indeed, the d gamma dt equals 0 seems to be satisfied. Okay? Any question about that? Any question? If you have any question, please stop me. I mean, this is not expected to be completely known from undergraduate or even graduate courses, so it's perfectly fine to come up with questions and discussions. Please, David.
Does this happen on like all objects or only certain type of objects?
Whenever you have sharp edges, vortices will shed from sharp edges. If you change conditions on your object.
So if you
conditions mean flow speed, angle of attack, or something.
So if you were to have like a rectangular shaped brick,
yeah,
it would happen.
Rectangular
like
section,
yeah,
it will shed from the sharp edges. But if you have round, so if you have ellipse, for example, there will be no shedding, or it will be very, very weak. Yeah.
So may I ask how was this picture taken?
Oh, the camera is moving with the undisturbed flow.
I mean, is there any special effect, or you just take a picture of the flow and it looks like this?
There is, what do you call it? The particles.
Oh, yeah.
There is, yeah, the metal particles, very tiny particles. I don't remember the name now. Yeah, they are typically used for flow visualization. And if you have a water tunnel, things become clearer. You can do it with smoke as well. In wind tunnel, it will be very easy to do. Any question? Okay, so we're done with lecture 1 and what is unsteady aerodynamics. Hopefully everybody has some idea in mind about what do we mean by unsteady aerodynamics mathematically and descriptively. We're going to go to lecture 2, starting with the governing equations, of course, for a general fluid. What are the governing equations? What are these? What are the governing equations for a flow? What are the governing equations? Come on. What are the governing equations, guys? Yeah. So we have continuity d rho by dt equal plus rho nabla dot u equals 0, which for incompressible fluid means rho is constant. So you get the second term equals 0, right? Nabla dot u. So this is continuity for incompressible fluid. Okay. Just divergence-free velocity field. Momentum. What is the momentum equation? By momentum, by continuity, we're saying that we cannot create more mass or get rid of the existing mass. Right? Mass is conserved, so this is continuity. It's simply mass conservation. By momentum, what do we mean? What's the abstract form of your momentum equation? What's the hand wavy form of your momentum equation? What's that you learn in high school, indeed? What's that? What's the hand wavy form of your momentum equation? It's just F equals ma, your Newton's second law, right? And just have this in the back of your head. If F equals ma is not correct, then this will not be correct as well, which we indeed do in our 241 sometimes. So we have rho du by dt equals negative nabla p. I will not drive the rest of those equations, of course. Hopefully you've seen it before. And we have here nabla squared u. You can see it clearly here. This is mass times acceleration, right? So rho is the mass per unit volume. So this is indeed mass, and this is du by dt. This is acceleration. Mass times acceleration equal forces. The right hand side is forces. We have two types of forces at least. We have pressure forces, and we have viscous or shear forces. Okay? Any question about that? Any question? Okay, so this is F nothing but F equals MA. So let's see. What is d by dt, large d by dt? So this is what we call the total derivative. Let me spend some time with that. The total derivative, d by dt, of any function, maybe f, function, scalar function f, is simply partial f, partial t. This is what we call local derivative, plus u dot not life. This is what we call convective derivative. Just to explain this, f can be any scalar function, okay? Maybe temperature. So if we have here some domain, and let's look at the temperature field. So at t equals 0, we have the temperature equal 10 Celsius, and at t equal 1 second, the temperature equals maybe 20 Celsius, and the temperature is equal everywhere. Okay, the temperature is equal everywhere. There is no spatial variation of the temperature. So if you have a particle here that is traveling, while traveling, I need to know the change of its temperature with time. What's that? Well, while traveling, nothing changes because the temperature is the same everywhere, so this motion actually doesn't affect anything. But the fact that the temperature itself varies with time, you just take the derivative with time. So partial your temperature, partial time, right? Which is, I mean, approximately, we can approximate it by maybe 20 minus 10 over 1 minus 0, right? Something like this, okay? On the other hand, if you have the sphere, the Earth, maybe here we have, along this line, we have the temperature equals 10 Celsius near the North Pole, then it gets hotter when you go towards the equator. Maybe here at the equator is 40 Celsius, okay? And I have a particle